great to be here.
All right, you guys. So maybe we could start getting into our seats. Does everybody have a place to sit? All right. So I think. Excited to introduce you guys, Gabriele and Jeremy. These are both MIT graduate students from the EECS department. They've been doing a lot of exciting work on bringing, I guess, molecular tools to all y'all. I think last year they gave a talk on one of the ligand docking software. So now they're taking it to the next level, bringing Boltz to the world. Boltz to the world. So, and before I forget, we had some sponsors. So wanted to give a shout out to Raven and Twist. If anybody here has infinite money, want to donate more, you can buy more pizza for next time. So feel free to, I think, go to this QR code and donate. Yeah, and then we'll put your logo on here and you'll be famous. Or if it's an individual donation, it could be your photo. If that's it. All right, well, I think I'll let you guys take it from here. Thank you so much for coming here. So if anybody has questions, feel free to raise your hand at any time.
Yes, please.
And these guys will try to answer.
Thank you, Sergey, and thanks everybody for coming. So first of all, let me say, if one of you or more have been at one of our talks on Boltz-1 before, a lot of the slides are going to be in common, so sorry for that and repeating ourselves, but hopefully there's going to be some interesting discussions and other points that we can make that are going to be interesting. So with that, let's kind of get started. First of all, acknowledge this is the work in collaboration with a few people at MIT, in Tommy and Regina's lab, and collaboration with Genesis Therapeutics that funded some of our GPU. Okay, let's get started. So I guess if you're here, you probably at least have read the topic of the presentation, and so the topic is going to be Boltz-1, and this is our the model that we published a few months ago to do general biomolecular structure prediction. As a very quick introduction, I assume many of you know a lot more about this than me. But we went from 70 years ago, kind of the first biomolecular structures, both of proteins and DNA, kind of being observed and resolved, to over time, the creation of the PDB, and with that, the gradual, initially exponential, now it's more like linear growth of the PDB, and this was really the critical component that led in 2020 to the breakthrough from DeepMind, solving quote unquote single chain protein structure prediction with AlphaFold 2. Obviously, we all know about the Nobel Prize. And then in May 2024, they announced AlphaFold 3, which went beyond AlphaFold 2, now predicting the structure of any arbitrary biomolecular complex. So containing proteins, RNA, DNA, other kinds of molecules. And unfortunately, they decided initially not to release the code. Eventually, they did release recently the inference code with some non-commercial license. But starting kind of from last summer, we really wanted to push beyond what was the state of the art represented by AlphaFold 3, and we realized that in order to do that as a first step, we needed to kind of replicate the work in order to have a working training regime, a working data regime that we could push beyond. And so the initial component part of Boltz, the Boltz project, was replicating AlphaFold 3, and then as we'll discuss, we did a few improvements and built a few observations that we think might be useful. And I've released it all, and it was the first kind of fully open source model reaching kind of AlphaFold 3 level of accuracy, as we will discuss. So let me first give a very quick overview at some of the key features kind of characterizing AlphaFold 3, and in particular, I assume most of you are familiar with AlphaFold 2. And so the two biggest innovations from AlphaFold 2 to AlphaFold 3, on top of training with all the remaining part of the PDB on all the other structures that were parsed out, in AlphaFold2 is that they moved from a regression-based approach to a diffusion-based approach. And this is really useful because especially when you start dealing with complexes, and especially complexes that have flexibility and don't have a lot of evolutionary signal, you start to have a lot more uncertainty. And if you have uncertainty, if you deal with a regression model, what you end up with is some kind of averaging that leads to pretty bad results. And so the diffusion model allows you to go from a regression-based to a generative-based approach, where you are now sampling your posterior distribution, and you can take a few samples and then use your confidence model to decide which poses best. For those of you that are not familiar with diffusion models, I'm sure you have interacted with diffusion models. These are all the videos and images that you see, AI-generated videos or images that you see on Twitter and the other social media. Probably a good part of the Super Bowl ads were created with some diffusion models. And the way that they work is, so in general, when you're building a generative model, you are figuring out a way of mapping a simple distribution that you can sample with your computer to a complex distribution that in this case is represented by biomolecular structures. It can be also images, videos, and so on. And so different generative models differ by the way that they define this mapping and the way that they supervise the model on these mappings. And so the way that diffusion models work is starting from an observation that is, if we take a distribution, and in this case, I'm using this simple 2D distributions, and we add noise, we go from a complex distribution to a simple distribution. In particular, in Euclidean space is a Gaussian distribution. But and these I can, there are many functions on the computer to sample them. And then the idea is that I can train a neural network to learn what's called the score of this data distribution. And so this is basically the gradient of the density of this distribution. And this is the vector field that I'm showing in this animation. And once we learn the score, we can use these results that was proven in the 80s that allows to basically reverse this diffusion process. So run the process in reverse using the score in this stochastic differential equation. And so we can go from an arbitrary kind of Gaussian distribution to our data distribution. And so the way that this plays out in AlphaFold3 is that we have this trunk that is where actually still most of the computation occurs with this kind of different recycling steps. But then these features from the trunk are passed to this denoising model that is a transformer-based model. And then this denoising model kind of denoises, and this is the score model, what I was calling score model in the previous slide, denoises our initially random input, producing a structure. Then the features from the structure, oh, I forgot I need to stay close to here. The feature from the structure from the trunk and the structure are passed the confidence model that predicts the confidence for the different predictions that we can make. And so we can take several samples and, for example, rank them with a confidence model. The second innovation was actually this atom-to-token kind of coarse grading. Now, when they moved from just dealing with proteins to dealing with arbitrary biomolecular structures, there is a lot more complexity in that you no longer have just 20 building blocks, but you really have a very large kind of multitude of possible building blocks, and building blocks is even unclear what it means. And moreover, so you could say, okay, we can just use atoms as our building blocks, but then the problem is that these models become very large. And so what they did is basically they alternate these two different resolutions. They have certain parts of the architecture that work at atomic resolution and certain parts of the architecture that work at what's called token resolution, where a token is an amino acids for a protein, is a base and is nucleotide for DNA or RNA, and is an atom for other molecules. And so you can see kind of color-coded that the different parts in the architecture kind of alternate operating at atomic level and operating at token level. And so this is a couple of key innovations that AlphaFold did. We'll see more the results later, but set a new state of the art basically in every kind of specific biomolecular structure prediction category. And so this is kind of where we started. Getting to actually Boltz-1. So the key contribution that we did was a few architectural and structural improvements / differences with what AlphaFold 3 kind of reported. Here, a lot of the parts were things that AlphaFold 3 didn't report. And so, you know, a lot of the things, for example, around kind of cropping, around kind of the way of pairing MSAs and all these kind of things, we had to sort of like experiment and try to figure out kind of how to do it best. And then there were a few things that we kind of noticed that we could improve that we integrated in the model. And I'll show you a couple of examples later. But then the main contribution is, I guess, you know, actually scaling up this model and being able to train a full-size model, kind of reaching AlphaFold 3 level accuracy. And then finally, we are also the first to release actually the whole training, you know, code and pipeline to actually replicate this. And Jeremy will talk about the work on, you know, actually parsing the PDB, which is pretty messy. And, you know, we open source kind of all this work and, you know, hope that nobody has to do it again. So a couple of examples on some of the things that we change over AlphaFold 3. So I mentioned this confidence model. So originally, actually in AlphaFold 2, this confidence model was something that they added, you know, after training the model. They realized that it was simple layer kind of prediction, taking this PLDT. They realized that it was actually really useful. And a lot of researchers started to use it in a different context, whether it's to predict, you know, what is more or less structured, you know, sometimes it's used to predict kind of binding and all these other kind of components. And so in AlphaFold 3, DeepMind decided actually to increase the size of this confidence model from, you know, just a single layer to having what's called 4 layers of this performance. So this is a relatively large block, so much larger model component. But we kind of took this kind of a bit further and says, okay, can we potentially even make this larger? Can we actually get, you know, better confidence predictions? And we saw that actually changing the architecture and making it similar to the trunk where it operates directly on the input sequence was actually quite helpful to improve the confidence outputs. This also allowed us to take the inspiration from what's done in large language models, where when you train a reward model, you basically use the pre-trained model and basically fine-tune with a different head to predict your reward. So in a similar way, we train the trunk with the structure output, and then we took this pre-trained model and fine-tune it for the confidence task. And so this provided, you know, faster convergence and better convergence. And finally, we are not only taking features from the trunk of the architecture, but we're also taking features from the different kind of recursive step. And part of the reason here is that especially when it comes to kind of binding interactions, actually a lot of the understanding of kind of the interactions doesn't happen in the trunk, but happens in the diffusion model. And so we found it to be useful to pass features that were produced in the diffusion model to the confidence model in its initial layer so that it can reason on them. And so these are like three innovations, and this is kind of the general architecture that we use for Boltz-1. And with that, if there are any questions, I'm happy to take them on the model and kind of the architecture. Yes, Nick.
So if I'm understanding correctly, the confidence model is the same size as the trunk.
Yeah.
It's interesting. It seems like it's almost too big.
So first of all, like it's the same size, but like the trunk, it doesn't do recycling. So the trunk does kind of typically, 5, 10 recyclings. And so that arguably it's, 5, 10 times smaller in terms of like execution time, but in terms of parameter count is the same. Yeah.
I guess I'm just wondering if you try to train this confidence model of this size without initializing the weights, what that trunk was after training, if you were able to actually train it, or if it was just too big, if you really needed to initialize the weights from.
So we didn't try on the full size model. Largely, we basically had. Yeah. So the question was, did we try to actually train the full confidence model without initialization, and whether it was too large to train directly? And the truth is that we did a few of these experiments on the smaller size model, something like 12 layers, something that we can experiment with the compute here at MIT. For the big model, we kind of had one run at it, so we didn't do this kind of experiment. But in general, like we were seeing even before introducing the initialization that having kind of going from, for example, 4 layers to 12 layers was pretty useful for the model. And here it's not necessarily, so there are 2 ways of evaluating how good the confidence model is. One is that basically looking at if I have cross different predictions, how well does my confidence correlate with the quality for different complexes. And so this is kind of useful to understand, if I'm making a prediction for a new complex, how good is this prediction really? And this is something, this is, for example, what has been kind of reported in AlphaFold 2, maybe also AlphaFold 3. Typically, you see very high correlation score, even 0.8, 0.9. A much harder task is when you take different samples from this denoising, to rank those samples. And the reason is that kind of, especially obviously in AlphaFold 2, even more because it was just a single layer and didn't even take the structure. But even in AlphaFold 3, it really relies a lot on these features coming from the trunk. And so these features coming from the trunk are in common to all the samples. And so, how are you going to do the sampling? You really need to use this structure output that's coming from the sample. And so kind of when looking at that, we were kind of really seeing that, with the 4 layers, we were barely getting any discrimination kind of quality, and scaling kind of the model was helping to, starting to be better able to discriminate. It didn't really help that much on the kind of overall ranking. That was already pretty good. Yeah.
Kind of in the same vein, do you have any kind of like intuitive takeaways from what the important aspects of shipping to this version of the confidence model is? Like, it seems like a very intuitive result that you take a very similar thing from the trunk as the confidence model.
Yeah.
From your experimentation, was there like a key aspect of that was the important part, or like?
I think they all sort of like added a bit. I think even just as I was saying, kind of we've seen kind of improvements across kind of all the things, scaling on its own, scaling and then adding kind of the pre-trained initialization and so on. So I would say it's obviously arguably you could say maybe this somewhat increases some of the inference time depending how many samples you take. So is it worth doing it? Obviously maybe you would want a smaller confidence model, it would be faster. So it's obviously a trade-off, but in general, we've seen that, giving more representation capacity, whether it's from initialization or whether it's from actually just the size of the model, kind of helps.
I think I missed something very basic about the trunk.
Yeah.
So say I'm doing de novo design, generative, I don't have an input sequence. Then what do I do? Like in Chrome, I'm giving it some shape or some constraint like that, and then they run it forward. What happens to the trunk?
Yeah, so I mean, obviously, this is not something that Boltz-1 on his own kind of is tackling. Here we are just looking at the forward problem, kind of, if you have a sequence, what's the structure? I can tell you, I think what has happened, and we are starting to see happen with Boltz-1, what happened with AlphaFold 2, which was and kind of Rosetta Fold, which is that for design, many cases, kind of these architectures have been either fine-tuned or kind of retrained to kind of do the design. And in those cases, you are basically feeding kind of empty tokens where, the model kind of has to figure out, and the model either is sampling what token, what, amino acid it is over the course of the diffusion, or it's just generating the structure of the course of the diffusion and then using something like protein PNN to actually generate the sequence. So this is kind of the way that we've seen this type of architectures being transformed into design models in the past. And without saying too much, this is something that we are seeing kind of already in a few applications. Sergey.
About the skip gradient, the upper and corner. It seems like, is this partially related why you might need the input sequence against the confidence model? I guess the intuition would be like, maybe the input sequence should be able to pass all the way through.
Yeah, so just to clarify, actually AlphaFold doesn't have, still has the stop gradient, but doesn't have the input sequence. So I do think that the input sequence is somewhat preserved. Actually, I'm not sure why. Okay. Actually, maybe technically there is also like a skip gradient here, kind of going from.
Hello?
Yeah, from here to here. So there is. One second, I'll count to the question online. So there is a skip gradient coming from here, from this representation to this representation. So I guess you could argue there is kind of the sequence being passed to the confidence model in either case. But for example, it doesn't operate over the atomic elements. All the confidence model in AlphaFold actually just operate at token level representation. Even the coordinates, we only pass the coordinates of the
Token centers.
Yeah, token centers. I think is C beta or proteins.
How different it out? Because I guess since AlphaFold doesn't use atom level input confidence metric, it's not able to then predict.
Yeah, it is it's kind of funny. It is potentially predicting. You can use it to predict at the level of atomic, but it actually never takes coordinates, input the coordinates at atomic level. So it's kind of somewhat inferring them, what it thinks, the model will predict. But if you change, some of the coordinates of, the atom outside of the C beta, the confidence model wouldn't say it. C beta for proteins, for other things is a different.
Where are the conditions? If you apply conditioners,
What kind of conditioners?
symmetry. Protein, particular protein fold from the data.
Yeah, so there are different ways that I guess one could integrate it. I think, in general here, we're mainly looking at kind of, sort of like, you could call it kind of blind predictions, whether you're predicting the structure kind of without knowing anything in advance. There are like some ways that people kind of try to do this is either through some sort of hacking of the template module here, or you can actually do this by biasing the denoising process. So that has been kind of done in a few cases, and you can actually be pretty successful at doing that, just hacking the inference pattern. So that's kind of the main ways that we can say.
You want to say something about pocket conditioning?
Oh yeah, there is also like a pocket conditioning. So for example, that's something that we added the AlphaFold as a similar model that they haven't released that also integrated pocket conditioning. So you can, for example, if you know that your protein or your ligand binds to a specific site at the other protein or DNA, you can specify that, and so you can sort of give in this input this gets fed into kind of the input, and so it's propagated through the whole network. Yeah.
Without Bolt-2, I think a lot of people have sort of noticed that before you even go into the structure module, eventually you have that field, right? That like those representations you generate.
Yeah.
The necessary knowledge. So you can just use the histogram, you can project out to the PTM or something like that. And so I know you mentioned that in a lot of binding cases, using this feature committee noise model was necessary to get confidences. So in your experience, is that not true with Boltz-1 that that a lot of the necessary confidence information is actually already formed before you go with the actual structure output?
Yeah, so two things, and I'll let also Jeremy maybe touch on this because he. Yeah, so I'll summarize the question. And so the question is, I guess I'll take it both at the level of predicting the structure and predicting the confidence. How much information is already in this final trunk representation versus, how much information do you need from kind of the rest? And so I would say two things, one on the structure prediction and the other on the confidence. So on the structure prediction side, this is something that we actually track during training, and it turns out that the metrics within proteins, so within like a protein chain or within a ligand, you can actually basically decode from here with a pretty good accuracy. But the metrics intra-chain, so between different chains or molecules, actually the ones coming out here are very noisy and not very good. So the diffusion model is actually pretty useful at, there is not that much uncertainty within each chain, but there is uncertainty in the way that the different chains are placed with one another. And so this kind of uncertainty gets resolved here. That kind of leads to the second point on the confidence. So yes, you can do a decent job at predicting kind of your general kind of PLDT, and that is somewhat correlated even out of here. But that's never going to be useful to, for example, rank different structures that you can create, because that doesn't actually depend on the structure. And so you really want, in order to take full advantage of the generative model that can, potentially you can run for longer, taking more samples. And AlphaFold 3, for example, has one pretty striking plot in their manuscript on antibodies, where they went to, I think like 5,000 samples and really got kind of improvements from scaling. In order to take advantage of that, you kind of need this structural prediction. Yes. Well, it is, so it's initialized from here, but then it does take in this representation. And so then it basically and then we fine tune the model. And so during this fine tuning, it's basically learning to combine, the knowledge that it already has about the structures with this, input from the structure to, learn to differentiate between different structure that it receives. Oh yeah, there was an online question. Happy to take it. Okay. They're saying hello, so maybe they were. Okay. With that, I'll leave the floor to Jeremy.
Okay, so I'll do a few things. So I'll show some predictions. I'll tell you about data, which was really like one of the big obstacles to getting this working, and results as well. We have, since the last talk, we did add a bunch of AF3 results, so you can actually see that. But yeah, just to, I guess, convince you that the model sometimes can do cool things. So this is an example of a structure, obviously, in the test set where it's able to like recapitulate the ligand very well. It's able to do some fairly large complexes as well. So I think one thing to keep in mind about these models is that they're trained on relatively small crops of the structures. At the beginning, we train it on crops of 384 token. A token is amino acid residue, and ligands are tokenized per atom. In the second stage of training, we trained it all the way to 512 tokens. AlphaFold 3 actually went all the way to 768. We didn't do that. But despite being trained on these like relatively small crops, it's able to still predict like these like very large complexes, and in some instances like very like symmetrical complexes. So when evaluating, we took a subset of the PDB that was after our validation cutoff, and we also restricted that the test set could only contain sequences that were at not more than 40% similar to proteins in before the validation cutoff date, and then we did an 80% Tanimoto similarity for ligands. That led us to like 541 targets. And we benchmark against Chai1 and AF3, which are both state-of-the-art structure prediction models, but much more closed source in terms of like model code, training, and data pipeline. And I'll do my usual joke here that, you know, partly, I think, thanks to us making the model open source, Chai also decided to make their model open source after the fact. So not only you can do open source work, you can force other people to do open source work as well. Except Google, yes. They have bigger fish to fry. We match MSAs, we match recycling steps, and we match the denoising steps, right? So there's the recycling of the trunk, but there's also the steps that happen in the diffusion. And then we do 5 samples, and then we evaluate a few different ways. One is we see what is like the best possible structure that we get out of the 5, knowing the ground truth. So that's sort of like the upper bound if you had a perfect confidence model. And then the second one is which one our confidence model thought was the best. As you'll see, there's like a bit of a gap between taking something random, taking something that the confidence model thinks is really good, and like taking the oracle, like the best that you could. All of that is released, including like the evaluation code in our repo. So looking at small molecule, and you know, the general message here for like the few plots I'm going to show you is that like, you know, the results are essentially the same across the different models, maybe AF3 with like still a slight edge over the other two. And here we look at LDDT-PLI and RMSD-on2. So this is for protein small molecule. LDDT-PLI, which is more like a distance kind of metric, and then RMSD, where we align the proteins and then compute the RMSD against the 2 ligands. Yeah, so yeah. I think generally it's like that there's, from what I've seen, it's a bit of both. Like there's some where like it's by a few points, and then there are instances where AF3 gets one much better than we did. There are instances where the opposite is also true. Like we found structures that we predicted better than AF3, but generally like if I were to pick all of the ones where there's a big difference, it's more often time AF3 that has it the best. Now, why this is the case, you know, I think there's a lot that went into that model, like even like, you know, more training, arguably probably like better data cleaning than we did. I think there's a lot that goes into it that might explain like the few extra points, but yeah. Yeah.
Models are right. But you just, let's say you select it based on
Like took the AlphaFold 3 structure.
your confidence, the Boltz confidence. Cases where AlphaFold got it right versus you guys got it right, tell the difference. Predict which is the
I'm not sure, to be honest with you. We didn't really look at that. Maybe. The problem is like the confidence scores are like very much like not calibrated to each other. So you probably would have to do some degree of calibration first to be able to compare them. But maybe if you did, then you could look at that. I haven't looked at that. Yeah. Yeah.
what is the difference between top one and one?
Yeah. So Oracle is I take the 5 samples, I compute the metric against all 5, and I say which one was the best. As if I have the perfect confidence model. I could always pick out the best structure that I predicted compared to the crystal structure. And then top 1 is which one did the confidence model thought was the best. And so I think what I'm trying to show you here is that like the models are like better than what it's able to pick. And like if we can make the confidence models better, we can also hopefully improve the metrics. And if I were to show you like I guess it's not on that plot, but like if you were to see like taking a random one, it would be like somewhat like, I would say like top 1 is somewhere in the middle between taking something random and taking the best. So it's doing something non-trivial, but it's not amazing either.
Makes me think, like, is there something systematic going on? Like, why would it sample the correct or more correct
Yeah,
protein ligand sort of interaction? I
Yeah.
assume it's what PLI
yeah.
stands for. But then rank it lower.
I mean, I think there's
than
like,
some other pose that's
yeah,
more incorrect.
I'll let you complete, but I
Is it
think,
because there's like
I-
flashing, like, what is, when you look at the structure?
yeah, I think there's two things. One is like the confidence model is not perfect. That's answer number one. Answer number two is you could imagine situations where like maybe there's one element that is like really bad for the confidence model, but yet the rest is like slightly better in terms of like RMSD. And so you end up picking the other one because there's like that one thing that he really doesn't like, for example. So it doesn't necessarily always perfectly align, you know, with the metric. So I could see like situations like that be possible. I don't know if you have other,
Arguably, the upper bound is not perfect. Like
yeah,
even like if you had a perfect confidence model, I mean, in practice, there is some randomness in the way that you crystallize that's not fed into the model. And so, you know, how do you choose, you know, between the different poses? It's
yeah,
like, so
that's
that
also
the top, you know, you're never gonna be able to reach the oracle.
I'm sort of just wondering if you, some of the things that we've looked at before with like with surrogates, we train a model. And the model says, oh, the model is wrong and for some prediction. But then when you look at the actual data, you look at the electron density, you look at the structure modeled into the electron density, and it's actually the model that's wrong. And so something shouldn't have been modeled into there. And then so the PDB structure itself should have been altered.
yeah,
And I'm
yeah,
just wondering if like, how much of the, anyway, we can talk about this later, but
yeah.
I'm sort of curious where it goes wrong, how it's going wrong. Cause it's just, it seems sort of.
I think we're not there that we can blame it on the crystallographist, the mistakes of the model, but I think there's still, but I think, yeah, I'm saying that, you know, yeah.
Well, just curious that the confidence model is saying that the more, it samples the right, more correct model. And then the confidence model says this is less correct. Anyway, so it's a fascinating.
Yeah.
Did you, aside from the sequence similarity column, did you do any comparisons structurally between the test set and the training set to getting intuition, at least from the protein chain side for?
No, yeah, no, we kind of followed AF3 pretty closely there and didn't really, like, yeah, arguably that would be like a good thing to do. I think if like your sequence similarity is like aggressive enough, like it's not like too bad. But that would be interesting to look at.
There is a very recent, I think last week, preprint from the group in,
Where the people do that help organize CASP,
yeah,
right?
it's in
Basil?
Basil, that looked at this and basically stratified the results in the test set by some different levels of similarity, and they integrated also a lot of structural similarity on top of sequence and similarity of the specific pocket actually for a small molecule. For
A larger one,
basically
actually? Yeah.
a superset. So they
Yeah.
they stratified for they didn't kind of have a cutoff, they just stratified the results.
Which I think is generally also like probably a good thing to do, like as opposed to just making a really hard test set to kind of show like what the results look at different bucket of similarity. So yeah.
I guess aside from that, was the test itself biased in any particular structural direction or towards any complexes of some kind or?
I think we did find like a little bit of bias on the ligands, right?
Yeah, so it turns out that if you bias to anything that is different, that was, you know, you get some pretty weird ligands. So there are not that many, you know, drug-like ligands in our test set. You know, a lot of them are pretty weird. So yeah, I guess that's at the end of the day, you know, I think, you know, it's probably interesting to have different, you know, evaluations on different specific classes of targets and ligands. You know, here we just try to be kind of different from the training set and evaluate them.
Yeah.
Did you change it
to like your confidence model, did you see that like the gap between Oracle and top one for Boltz was?
So like Gabriele said earlier, the tough part is that I'll say more about that later, but we only got one shot at training the big model. So a lot of the experiments that we did on that were like at a much smaller scale. So like doing that experiment it just wasn't possible, but yeah. If we have more GPUs, we can try more things, you know, but yeah. That's the tough reality. Protein, again, it's like kind of similar message. We see, especially on like the higher quality ones, like again, like AF3, performing a little bit better. I mean, it's all like within like a few points. And we do see still a bit of a trend, right, in terms of Oracle and top one, but not as actually as significant as we see on ligands. Yes. I mean, as far as we know, it's the same, right? So we know the date, we know the filterings they did, we matched it as close as possible. You never know. Yeah.
The size of the difference between top one and Oracle for the different models, or does it seem like they're relatively similar?
Yeah, I think we've seen that it's relatively similar actually across the models. Yeah.
Because sometimes you get like a low confidence, right? Maybe go very low XTM. If you were to like remove all those from these predictions, do you see that performance go up? Or are these all like, 0.9 confidence or whatever?
Yeah, no, we actually just completely randomly sampled. Did we take the top 5 out of 25? Or?
I think the question is, so I think the question was more, if you only took the structure where the model is confidence, would you see much
Yeah.
higher quality? And the answer is yes. You would
have this valuation somewhere like, how often?
Yeah, that's what I was saying.
I don't know if we have, it's definitely very easy to obtain from the results that we've published.
Yeah.
We put out, we have a CSV where you basically can take for all the models, the confidence and so on. So it's very easy to obtain. But this was, for example, something that was, I think in the AFL3 paper.
Well, in the AFL3 paper, at the very least, they did like a bucketing between different IPTM buckets and then showing the trend of the performance as a function of the IPTM confidence. So I would expect a similar trend here. There was at one point we did do something where we like sample 25 and take top 5. I don't remember if like that ended up.
Choosing between complexes.
What do you mean? It was like sampling 25 just for that structure.
Yeah, it's choosing within that structure,
Yeah.
not across different structures.
Yeah, no. Not across different structures, yeah. I want to say no. Like, I think that there's been no evidence since even AFL2 that like templates make a big difference. Now, that being said, we did see a little result.
These results are without templates.
Oh, we did run AF3 without templates as well. Yeah, that's true. But we did see like actually in the people we talked to from Basel, they did show us like, so they're going to update their paper, but they did like the analysis of using templates and without of AF3 at the different like threshold of similarity to the training set. And there was like really no difference in like the sort of like right part of the graph or like things that are similar to a train. But on the left part, which was like the most dissimilar part, there might have been a tiny bit of signal, but it's a small data set at that point. So I don't know, I would take that with a grain of salt, but so I don't know. I think templates potentially can like maybe be helpful for something that's like, the model has like not seen in training at all. But if it's like seen that template during training, I really don't think there's much to it. Yeah. Yeah, great question. We're not really sure why they decided not to do that. And we've been thinking a bit about it.
Speculation why there might be that gap. I guess the other difference is the distillation set. You guys make one or?
Yeah, so we used the OpenFold one. So in the past, I've run experiments using like a 10 million size distillation set and the Boltz-1 one, and I hadn't noticed something really drastically better, maybe a tiny edge on using the 10 million one. So then when we went to do this, because we didn't want to run 10 million MSAs, we ended up just using the OpenFold one. So I don't know, my intuition is no, but yeah,
Crop size might be one.
crop size could be one. We did train a little bit less. They did like 120,000. We did 80 or 90K. Yeah, it could be a few different things. Yeah.
I guess if you plot one versus the other and color by length or something, or color by templates, or wonder if some things might pop up.
Yeah, yeah. We have been like, we're starting to do like more thorough evals and stuff recently. So, also on like subfamilies, also trying to see if like there's some families where it just happens to be worse or something. So hopefully I'll have a better answer to that question soon, but yeah. Okay. So full atom performance now also incorporates like DNA, RNA, single chain protein. Similar message, not gonna rehash. We've made the repo hopefully as easy to use as possible, and then we also integrated the MSA servers from CollabFold. So thanks Sergey, thanks other people involved in that. It's really like improves the user experience so much, I think, to not have to wait 10 minutes for your MSA to be done. So the MSA runs in a couple seconds with the CollabFold server, and then we do the prediction using that. Actually, we also used CollabFold to generate all the MSAs for training. So we did not use the typical jackhammer pipeline that AppFold uses. And I mean, I guess this comes to show that those MSAs are great and you can train really good models with them. Do we what, sorry?
Even though the score that I'm on the same right there, the actual structure that you get is pretty superior back no discrepancy.
Between like using the CollabFold MSAs or using jackhammer MSAs? I mean, here I'm specifically talking about, we use those for training initially. So I think for training especially, it doesn't matter as much. I mean, maybe Sergey can say more. My general sense is like that the CollabFold MSAs are very strong. There might be some instances where if it's very, very, very shallow MSA, maybe jackhammer finds a few more, and that can be impactful. But I think for the vast majority of inputs, that's not the case. I don't know, Sergey, if you have more to say about that, but yeah.
Like sometimes one's better than the other.
Yeah.
Like say thousands of different ways and trying to get a single one.
Yeah. Yeah. Right.
You say CollabFold MSAs, you mean MCs?
Yeah. Yeah. So some of the things we did that you cannot do in the F3 repo. So pocket conditioning, the full processing and training pipeline. We do multi-GPU batch processing, so you can like do a large number of predictions across your GPUs. We have the fast MSA computation with CollabFold and many more things in the works. Okay, so a few things about data. Like ultimately, like one of the big challenge with doing this is sort of understanding all of the nitty-gritty that goes into parsing the PDB data for a machine learning application. So the first one is constructing MSAs can be very, very expensive. So with MM6, we were able to create MSAs for the whole PDB on a single node in under 2 weeks. So potentially also you could parallelize, you could do it really, really fast. So that was sort of a lifesaver for us. And I believe we might have been the first to train a model like that with only CollabFold MSAs. I don't know if that's true, but it might be. Handling assemblies was quite challenging. So AlphaFold has, the PDB has different assemblies for a deposited structure. And for some obscure reason that I don't fully understand, information is sort of spread across assembly files and amongst other files. And it's really hard to like get everything in one place. And covalent ligands with this concept of leaving atoms is really tricky. So the way that the PDB organizes ligands is that it has this dictionary that gives like codes to them, 3-letter codes. And then you have this dictionary that maps these 3-letter codes to you can basically reconstruct like an RDK molecule from. Now, the problem is that code gives you sort of the atom composition of your ligand and the bonds. But in some cases, the ligand is found in different conditions. And maybe it's covalently linked. And so some of the atoms are not in there. And in some other cases, it's non-covalent and you have the full atom. Now, there's a lot of ambiguity because there's this list of leaving atoms that they give you. And what we do with AF3 is we just say, okay, if it's covalent, I'm just going to remove all of these like leaving atoms. But I actually believe that there's like situations where things remain kind of ambiguous, where things can be a leaving atom in some cases, but not others. And ultimately, like because the atoms are not always guaranteed to be resolved in the PDB, it's hard to know sometimes if something was just not resolved or if it's not in the actual molecule. And so you end up kind of guessing around at what should be like the canonical input to the model. So yeah, this is something that I found super frustrating to think about. Yeah, for some reason also a lot of the PDB MMSIFs don't have the bonds of the ligands. So you have to go back and use this dictionary. Anyway, it's pretty painful, and we've tried to make it simple so that you don't have to do it. So we released the MSAs, our preprocessed data, and the data pipeline for people to use. So a few words on limitations, and then since then we've made some progress on some of those, so I'll talk a bit about that. So yeah, one of the things that we found is that when there were two large symmetrical chains, occasionally the model would just like put them on top of each other. Since then, I think that I actually wrote a bug in the in some of the data cleaning because that actually happens in the PDB. There are models deposited in the PDB that have overlapping chains, which is unfortunate. So you have to be quite careful. This happens also for ligands. Actually, it happens very often for ligands. So you need to be very careful with like how you clean the PDB. Performance on nucleotide protein complexes remains limited. I think that's one of the problems I would categorize as like still very hard to solve. Like, AlphaFold did like a lot of like self-distillation and things like that, which, improved the numbers a little bit, but the reality is like there's just not a lot of high quality data for like RNA, DNA, protein interaction. And so that remains still like kind of a low point of what these models can do. So we need more crystal structures of those. Memory consumption remains very large in these models. So currently in the repo, we support roughly like 2,000 tokens for like a 48 gig GPU or so. Now we've been working on that, and I think hopefully very soon we'll be able to like increase that limit. I don't exactly know to how much, but hopefully significantly. But that remains something that's like a constant challenge, not only for inference, but also for training. And with memory, also speed. Right now, we can fold things roughly in like 30 seconds to a minute for like an average size protein, let's say 400, 500 amino acids, which still makes like something like screening very expensive. So we do want to make these models faster. We already, again, some of the things that we did for inference also apply for training. So we've been able to accelerate the training of the model by like a few, like 2 or 3x now. And then we're hoping, an inference even more. So we're hoping to start to make more improvement there. Maybe I should say one more. One other thing also that that tend to happen quite a bit, where like clashes or like non-physical things in the ligands, and that's also something that I think we've found a good solution for that we're going to be releasing pretty soon. Okay, so a bit about what it took and where we go from here. So we trained the big model on 128 A100s for roughly 20 days. And the cost of that is like, it depends on your market price, but like roughly like $100,000, maybe a little bit less, a little bit more. So we really only got to do this once, which meant that we needed to do a lot of the experiments at smaller scale. And then while we were training the model, we kept on finding little issues. So we would like stop it, fix some things, restart from that point, and we did that like maybe 3 or 4 times. So it took like a lot of surgery and a lot of delusional confidence that it would work. And we did come out of it with something reasonable, so that was cool. But yeah, it's pretty nerve-wracking, I think, to do these things. So and I think that's the cool thing about the small scale experiments is that like to a large degree they do seem to generalize pretty well once you scale things up, but not always. And of course I should say that all of this is possible because of all the insane amount of work that's gone into creating the PDB, and hopefully like despite these models starting to like be pretty good at structure, I do hope people continue to make a lot of structures. We need more of those. So the next generation of models, I think, will continue to take a lot of compute. And we have been actually working with industry partners. So we did that for this model. We're continuing to work with industry partners, and that's proven to be a pretty effective way for us to acquire compute. Yeah. So I can say this one, which was Genesis. I can't say the next one, but you'll know at some point soon. Yeah. But yeah, I think like generally we found that industry is actually pretty eager to get more of these open source models out there. It's not always easy even for them to replicate these things internally. And so we found that they're pretty excited to give compute so long as they get a little bit out of it too, which, some PR and yeah. And some people involved also, they get their researchers to contribute and yeah.
And the models themselves.
And they can play with the models maybe a bit before. Yeah. Yeah.
Related to the partnership, I'm just curious how MLT is sort of collaboration.
Yeah, I don't remember exactly the history of it.
I was just talking to Evan.
Yeah.
We needed compute, and he offered to give us compute, and we were training the week after we were training the model there.
I will say this happened quite late in the project. So we were, I think, already had started to train the big model, and they really helped us get it to the finish line. Yeah. We were actually, so fun thing, we were using this big cluster from the Department of Energy, which is great. You should apply to it. It's great. But it does like have this like 48-hour limit. And then so you like train for 3 days and then you don't train for 2 days. And you train for 3 days and you don't train for 2 days. So you have to be extremely patient with that thing. So yeah, thanks to Genesis, we didn't have to do that at the end. Yeah. Yeah, absolutely. So yeah, for sure. And I think one of the things that we've like started to do that I wanted to mention is like we've taken a lot of interest in like fine-tuning the models, for example, for like different applications. And fine-tuning is not that cheap even, right? Like, I mean, you don't need to train for as long, but it's still a big model and you do want to feed pretty large batch sizes to it. So it's still like somewhat expensive to do. And so if people are interested in like specific fine-tunings and things like that, that's something we're really excited about. Beyond that, I think there's also
we're also setting up a collaboration around data.
Yeah.
So here we're mentioning structural and non-structural data. So yeah, so we are setting up with a few industry partners a collaboration into kind of sharing, and probably most of this data will be public, but there's probably also going to be some data that's used for training that won't be public. And so if the goal is really to come together and get the best model that we can, and obviously a lot of the improvements will be on the methodological side for the next version, but there's also going to be a lot of that comes from just more and better data. And so yeah, if other people want to kind of join the effort, would be the more the better.
I think there's also, if I can just add a little bit to that, like I think there's also this big question of like, what is the right data that will improve these models a lot? And so like, if you have data that you think is like, would be great to test, to see like the value of for these models, I think like we're pretty eager to even answer that question. Like, what is the data that we should be generating? That's non-structural, especially, that will help these models.
Yeah, I guess we're going to consider chemistry in the future.
What was that?
Yes, generative chemistry. Yes.
Yeah.
Yeah, it's not, I think, too much we can say about that, but yes, I mean, we're trying, obviously, trying to improve, structure prediction, but, also improve, some of the things that structure prediction is used for.
What type of non-structural data are you thinking about or excited about?
Yeah, so there is, obviously, there is lots of data about interactions they were interested in. Data, also there is interesting that quote unquote information about structures that is not fully a structure. There is kind of different kinds of kind of mass spectrometry data where you can find more specific for example contacts between protein interactions and so on that people have figured out. So there is kind of all this data in general about kind of, for example, interactions, about reactions, about things that kind of we're putting together to improve the model and the things that you can do, obviously, both this in structural but also beyond structural prediction.
One thing I'm going to think about is something that mentioned a few of the limitations of the real models. I think there's a lot of limitations of crystal structures themselves, which we're kind of freaking out to grant truth, but in order to get a crystal, we have to a particular soil concentration to truncate the N-terminus or point mutations and so on. And so that crystal structure by no means means that that protein actually exists like that in a bit of a cell, right? Which is kind of what we're ultimately probably a lot more interested in. I was wondering if you see when you do a testing model against, let's say, crystal structure versus electron-wise loss of data or something like that, whether you see any differences based on what NR, whether you see any difference on the accuracy of the prediction based on the experimental methods or something like that.
Yeah, I think for sure the models are somewhat biased towards crystal structure because that's the majority of what they see. And definitely, for example, conformational ensembles is a challenging component even for these models. That being said, I think there is we are trying to again even on the structural data integrate data from different sources. The reality, unfortunately, is that beyond crystal structure, there is really not too much data. I mean, obviously, there is everything else that there is in the PDB. There is a bit of molecular dynamics data that you can find around, but it's not really that much in the public domain. That's also something that we're trying to improve.
We did start to like do some evals on like some NMR data. We didn't necessarily see something super different there. No.
So I'm super interested in small molecule binding to proteins. And I'm wondering with Boltz-1, what were the small molecules that the model saw during training? Was it purely the PDB? Would bringing some of Cambridge structural database into the equation help? Is there a sort of a feature for constraint files on here's bond lengths, here's bond angles, these are rotatable torsions that would make the molecules more crystallographic or agreeable with sort of, if you have a quantum chemically optimized structure and you say this is right.
Yeah. So
I get that to work.
So there is, I think, a few layers to that. So first layer is in terms of, kind of, constraints, bond length angles that, as Jeremy was saying, easy fix. And this is something that, easy problem. This is something that we're kind of bringing soon. The second kind of layer is, can you integrate, and also what is the value of integrating kind of data, for example, from DFT and semi-empirical methods and something like Cambridge Structural Database into these models. Like, for example, AlphaFold Latum, sorry, not
Rosetta Fold
Rosetta
Latum.
Fold Latum does this. They doesn't seem to be that helpful. I
According
think
to them.
for some large molecules, and this is going to be useful. So kind of thinking like macrocycles, things like this. I think this is going to be useful because the model is still struggling. For kind of but for other molecules, I think the challenge on protein ligand complexes is more, and this is also something that we have seen even in our work, is more on the diversity of pockets and interactions that you see. So I see that as being kind of more the bottleneck rather than individual structures of ligands themselves.
For what it's worth, I think one thing that is interesting is like the model does take conformers as input, right? And I think in AlphaFold 3 case and in our case as well, like we found that it sometimes like doesn't respect some of like the input conformer, even in terms of like chirality, for example. So those are things that like we've largely fixed now. But it is, I think, somewhat telling that like the model is like, I guess, ignoring it to some degree. So maybe something to be done there too. For the conformers that we feed in.
No,
Yeah.
Yeah, no, we haven't done that. I mean, the model like knows like the charge of the molecules, but that's about it. Yeah,
It's probably a whole new level of complexity into parsing the PDB.
yeah. I mean, you
But
could,
if someone wants to do it,
yeah. I mean, you could argue you could like feed like pH and like a bunch of like conditions on how the thing was done. Like, you can take that pretty far. I don't know. Yeah.
Seems that already affects that training, the MSA generation. But a lot faster. But at inference time, you also have to have a lot of time spent on MSA generation. Would you do any other stuff for MSA stuff like on the ESM?
I mean, with MM6, the MSA takes 1 second. So it's like a minority of the compute time. So
Or single chain, but
yeah. I mean, okay, like I mean it's some time, but it's like it's not like it's never a large multiple of how long it takes to do the structure prediction in the first place. So I don't actually think there's like that much value in using like the no MSA strategies. Yeah.
you think that that's not a way to get the model down. So, because a lot of my biologists don't work on VPCs or certain servers, they work on MacBooks and laptops. So
Yeah.
That architecture way to get needs.
Well, I mean, this is the great thing about the CollabFold server, is that you don't have to run it on your computer. So yeah, thank you, Sergey, and others. Yeah.
can I say one thing? So obviously, manuscript code Slack channel might be, this link might actually be expired. So if you go on the GitHub, there is a non-expired link to the Slack channel.
Sorry.
We have like 750 people. It's been really cool seeing kind of people interacting. Last week, we had Tim posting some very cool results on antibodies on the Slack channel. So please join and, yeah, share your experience and your bugs.
We're also in the building next door, so we're not far if you ever want to talk. Okay, thank you.
Gabriele, thank you so much. They're gonna be here for a few more, I don't know, minutes or 10 minutes or.
Yeah.
Yeah, as long as it takes.